Rigify 的外挂打开来哦，所以在 Preferences 偏好设定里面呢，这边的 Add， 你必须要搜索这个 Rigify， 然后打勾，这个地方才会出现哦，出现这些东西哦。那出现这些东西以后呢，我们来讲一下这个一些设定啊。首先呢是这边你会看到所谓的 FK 跟 IK 哦。IK 跟 FK 呢，它通常所代表的意思是像，比如说一个是 FK， 然后 FK 的话呢，通常讲的是 forward kinetic， 就是所谓的正向关节哦。forward 不知道有没有打错，不知道有没有多一个啊。然后再 IK 哦，IK 是逆向关节 inverse kinetic。那它分别代表什么呢 ？kinetic 是不是少个 e？ 分别所代表的意思是这样子，像是所谓的正向关节，它的意思是说，比如说我现在有一个关节长这样，然后呢，这里有一个点，我必须要到达。那到达的时候呢，我要旋转关节呢，我必须要一根一根转。第一个要先转这一根，然后末端要到达，我可能还要再转这一根，一根一根转。所以呢，就是像这种，大概我们就叫做正向关节，就是一根一根转。那逆向关节的作用方法不太一样，逆向关节的作用方法是本来你的关节长这样，但它这个地方会多一个叫做 IK handle， 反正就是叫 IK 的 IK 的一个把手。然后这个 IK handle 呢，比如说我现在要到达这个位置，那这个 IK handle 是长这样子，它可以直接移到这个位置来，然后它会去计算这个关节要怎么旋转，所以它会直接去算第一根关节怎么转，第二根关节怎么转，然后就直接到位了。所以 IK 在某些情形下比较方便，有些情形下是 FK 比较方便。所以一般来讲呢，我们在做动画的时候，走路的话，手臂的摆动我们会用正向关节啊，逆向关节会用在脚趾着地之类的东西，就是说它的末端要跟一个地方贴在一起，固定一段时间的，我们都必须要逆向关节。所以 IK 跟 FK 是使用时机是不一样，一个叫正向关节，一个叫逆向关节哦。所以你看到这边有 FK， 这边有 IK 哦 ，OK， 所以手臂的 IK， 然后 FK， 然后脚的 IK， 脚的这个 FK 哦，这个大概是我们第一个要先跟大家说的哦，什么叫正向关节，什么叫逆向关节。所以你做一个动画，比如说有一个人站在捷运上面，他要手抓着把手，那个把手必须要跟他的手粘在一起，就必须要用逆向关节。那脚着地的话，因为他站在原地，那个车子晃来晃去，脚要站在同一个位置，也是必须要逆向关节。当他走路的时候，手臂的前后摆动，我们那个手臂就会用正向关节。所以手臂关节的正向、逆向大概是这样子。好，所以我们现在看到第一个什么，它的 rig layer 就是它的这个架骨架控制器的图层，大概分这些。一般来讲，我们不会叫 rig layer，因为 Blender 很多都不是常规的名称哦，所以这个跟大家说一下。接着我们这边呢，现在看到这里有个 root， 一般来讲 root 大家可能会有两种设计。一般的3D 软体呢 ，root 通常可能比如说它会说是 pelvis， 就是骨盆的位置。然后另外一种可能呢是下面这个地方，这个最大的控制器，去控制我们的角色要放在场景中哪一个位置。所以 root 这个根的意思哦，它可能会有两个，第一个是骨盆，第二个可能会是这里。所以这不一定啊，看他的高兴怎么设计啊。OK， 然后再来我把这个讲完，就让你就是稍微看一下，就是这个叫做 SYZ User。SYZ User 哦 ，User 其实它是一个观念，你一定要知道哦，因为它扯到一个东西，就是说所有东西在旋转的时候，并不是你想象中的那种旋转哦。这个我先存档，我开一个新的档案哦。像我现在旋转这个东西呢，它这边轴向会分几种 ，global 是以世界坐标轴为基准在转，所以你放开来以后，它看起来还是世界坐标轴，这个是世界坐标轴，就是 XYZ 这个世界坐标的一个标准定位方向。然后 local 一般来讲，我现在讲几个比较重要。local 是以它自己为坐标轴基准，所以你会看到这个轴向已经旋转掉了。OK。然后另外一个叫做法向量，那个就再说了法向量是完全另外一回事现在呢比较重要的是叫做 gimbal。gimbal 其实是所有的旋转其实都是背后都是 gimbal 旋转，背后都是 gimbal 在旋转。它会有一个就是说，它上面本来物件会有 S、Y、Z 三个轴，然后它旋转的时候，它会排一个顺序就是你在讲义里面看到它这边有一个 S、Y、Z ruler， 就是哪一个轴向是最上层，然后哪个是中间层，哪个是下层。这会扯到一个东西，就做角色动画的时候，它会有产生 gimbal lock， 就是东西没办法转，就是转不动了，因为它轴向已经卡在一起了。所以这个你听听就好了，因为我觉得你听完应该也记不起来，但是最起码知道什么是 ruler， 就是它是在排那个旋转轴的父子层级，哪一个层级最高，哪个层级最低所以这边要播影片给你看因为这个不看影片。
Hi, Amedeo Beretta here, and due to a conspiracy of factors, it's been a while since my last video.
In this tutorial, we'll look at Euler rotations and gimbal lock to see how strange motion can occur in between keyframes. In the last video, we saw that Euler rotations have a rotation order that can be changed with x, y, z values. We'll explore this further with a quick example of setting up the rotation order of an object to avoid gimbal problems. So how does Euler work? This gimbal machine shows us. Each part is linked to one another, so when the parts slide around, we can see how the rotations are passed on. By spinning each of the machine's 3 arms, we can rotate the jet into any angle. But notice when the jet points up, how 2 of the circular arms match up. This is exactly the same effect of gimbal lock, causing 2 circular arms to rotate on the same plane. Let's make this ourselves in a hierarchical system. To demonstrate, we'll grab some torus objects. They can represent each axis. Green will represent Y, X will be red, and Z blue. So altogether we have 3 toruses and an arrow object. Let's parent them together. X to Y, Z to X, and the arrow to Z. This is going to mimic a rotation order of Y, then X, then Z. The Y, or green torus, is at the top of our hierarchy. So in this parent structure, everything rotates with it. Z, on the other hand, affects the arrow, because it's at the bottom of the hierarchy, or the last axis in the rotation order. X is second in the rotation order, so it'll affect Z below. And see how Y stays still, because it's at the top of the hierarchy. Now here's where things start to get interesting. If we continue to rotate X in the middle of the hierarchy, it'll cause Y and Z to align. Here, this rotation order hits gimbal lock when 2 axes align. If we're animating, and our next step is to turn the arrow down, there's a problem, because there's no axis to turn on. Here's the missing axis, in grey. It's always possible to rotate our arrow into any new rotation, but we'll have to rotate all 3 axes to achieve it. Let's undo this and rotate all axes at once. Notice how the arrow doesn't rotate in a straight direction. Instead, it moves in an unexpected arc. This is the cause of gimbal problems in animation, because the object can move unexpectedly in between keyframes. A solution is to use a different parenting structure. This will change the arrow's rotation order. Our new order will be Y first, then Z, then X. In our new hierarchy, Y is still the parent, but X and Z have been swapped. Now we can rotate the object without hitting gimbal lock. In between, the arrow rotates as expected. But the gimbal problem doesn't go away, it just changes. With Euler, gimbal lock will always occur in some situation. There's just no way around it. In this example, gimbal lock still happens by turning the Z-axis 90 degrees to cause the X and Y axis to align. In another parent structure, the rotate order might be Z first, then Y, then X. Now gimbal lock occurs when the Y-axis rotates 90 degrees. Altogether, there are 6 parenting combinations to choose from. In each case, gimbal lock occurs on the axis of the parent, when the middle axis is rotated too far. Let's explore this in a real animation situation. Here's a 3D camera. We'll use the 3D software Maya as our example. In Maya, the rotation order is written backwards. In this case, Z is the parent, Y is below, and X is the child. Z here represents the role, or bank of an object. In this order, Z is at the top of the hierarchy. Y is in the middle, so when it's rotated, it won't affect Z. This axis can be referred to as yaw, heading, or pan. The bottom of the hierarchy is X, and in this example it's pitch or tilt. As soon as the camera looks sideways, we achieve gimbal lock. This isn't good, especially considering that the camera will frequently look to the side. In this scenario, it's difficult to roll the camera because Z, our roll axis, has been aligned with X, our tilt axis. If we switch to local object rotation mode, our manipulator will snap to the intuitive way of rotating the camera. But remember that this is only a visual guide. It simply makes it easier for us humans to rotate the camera. Under the hood, the software package is still using the Euler system, even if it doesn't appear that way. To demonstrate, let's roll the camera a little. Now we'll switch back to the Euler rotations and see what's actually happened under the hood. As we can see, the software, in this case Maya, has rotated the object with Euler rotations. In fact, it's always calculating in Euler, whether we like it or not. It's done this automatically and behind the scenes, matching how we turn the object using our local object manipulator. Euler is actually the correct display of how the computer sees the object. In this case, our camera's rotation. And this is all okay until we go back to the camera rotation before it was rolled. In this animation example, the camera isn't rolling on one axis. It's actually changing the values of 2 axes at once. This causes the camera to skew strangely in its rotation, and not just roll along its length. Let's reset and see if we can find a better rotation order. With any object, the key is to find a rotation order that has the least chance of hitting gimbal. So the trick here is to find the direction that the object is least likely to face. In this case, a camera rarely
结束了 ，OK。总而言之，这一段其实就比较不是软体操作，但因为你所有的3D 软体都有这件事情存在，所以必须要跟你讲。哦，下面换。